A very good afternoon to fellow participants of the Eurosteel 2020. Today, I'd like to discuss about our presentation topic on the response behavior of high-rise modular building under wind and seismic load. We are from the Department of Civil and Environmental Engineering from NUS, and myself, I'm a senior lecturer with the Department of Civil Engineering, and together with me as co-authors, we have a PhD student, Mr. Yi, research fellow Dr. Dai, and eminent Professor Richard Liew, who focuses on the PPVC and steel structural composite systems. The topic of the presentation will be on the introduction of to the content and the advance of the steel concrete composite modular systems used in NUS, and our global analysis of high-rise PPVC building, followed by the summary. Basically, PPVC stands for prefabricated, pre-finished volumetric construction, and typically it consists about six phases of work. So typically phase 1 consists of fabrication of the steel structural framework. Phase 2 consists of assemblies of sub-assemblies, like for example, prefabricated bathroom unit, installation of mechanical, electrical, plumbing services, and interior and exterior facades, which after that is being transported to the site by a lorry, and enter phase 6 for erection, and followed by exterior finishes, where in the phase 6, the joint technology is crucial. So a large component in PPVC, a large component actually is formed by a combination of pre-finished modules. So like for example, shown in this picture here, this is a floor unit, consists of a living room, bedrooms, kitchen modules, which are assembled together and built up in the tall building. And each of the module actually is transported by a lorry of a certain weight, width not more than 3.4, height not more than 4.5, length is about 40% of the motor length with a weight of less than 80,000 kilogram weight. So what are the benefits of PPVC? Mainly actually is through this technology, there's actually savings in construction time of up to 15 to 20%, savings in manpower up to about 40%, better quality assurance and quality control, improvement in construction safety and hence a working good and working environment, followed by sustainability and allowing for promotion of the factory automation. So this is actually in line with our BCA Industry Transformation Map 4.0, which actually focuses on improving in productivity with all these benefits. So the benefits also come with challenges of the PPVC currently, where there is actually the heavy weight and high rental cost of high capacity crane. Research actually shown that as of 2020, initial cost and rental rate of tower crane above the 30-ton capacity actually is responsible for 15% of the PPVC project total. So another challenge is there's a large number of modules, and also overly large thick columns and small clear height. Okay, all these actually also together with the coronal construction. That is why we have actually been researching on the advantages of long span PVVC modules, where we combine these two 6-meter module to become a 12-meter module. And typically the weight of a single finished PPVC module consists of 1/3 is the steel skeleton frame, 1/3 actually is the floor material, okay, and followed by the wall material. That's why we actually focus later on in the floor material. We use a slim floor, lightweight flooring system to reduce the 32% of the weight. So in our NUS PPVC technology of a steel concrete composite module, the key aspects that we are actually using actually is the lightweight flooring system, long span modules, reduced module headroom, novel connectors, and we did checks on robustness where provision of adequate vertical and horizontal heights are provided. This is a sample of a composite module spanning up to 12 meter. And it actually consists of slim floor, lightweight concrete slab. Okay. And the picture here shows you a sling roof slab. And this is actually the rectangular hollow section, and the width is 3.4. So in our advanced steel concrete composite PPVC systems, as a composite, some of the technology innovations that we have actually created in partnership with the National Research Foundation, NUS, and Sembawang Corporation in Singapore is we have actually created some lightweight concrete with expanded shell, a slim floor system using steel fiber reinforced concrete slab without rebar, and created ultra high performance concrete for grouts using fly ash or GGBS for industrial races, and also innovated on grouted sleeve connections for intermodular connections. So some of the technologies actually have been adopted, for example, in using the slim floor system using uh, SRFC slab with no rebar, and where we use a lightweight concrete. Okay, so and the portion of the right hand side rectangular hollow section column filled with concrete, we also use high performance concrete, and we also innovated on grouted sleeve connections. So on the lightweight concrete development side, we have actually developed concrete of up to easily 1008 kilogram per meter cube with a compressive strength of 50 megapascal. And these are actually the price of the lightweight expanded shear aggregate was about $50 to $80 Singapore dollars per ton before transportation charges. And this is actually a mixed design of lightweight concrete with expanded shear, where with a water cement ratio of 0.3, the content of OPC, silica fume, water, sand, coarse aggregate superplasticizer, resulting in concrete density of 1720 kilogram per meter cube, and the 28-day compressive strength of about 53.5 megapascal. And actually we use this into the slim floor system, and combined also with steel fiber reinforced concrete slab with no rebar. This reduce into less manpower cost, up to about 2 times faster slab construction time, and 20% lower dead load, and up to 30% reduction in overall cost. And for example, this is a conventional RC slab for a module, which actually we propose a steel fiber reinforced concrete slab. And we did a test of this SRC slab and compared with lightweight and normal weight, and it has a adequate moment capacity versus deflection curve. And the capacity of the slab at ultimate, the capacity of slab easily exceeded the ultimate load limit straight capacity, and the deflection of the slab at SLS actually is within the limits. Okay, based on a typical live load of 1.5 kPa live load and the superimposed dead load of 2.25 kPa. So for the ultra high performance concrete with fly ash, okay, we actually developed where a mix where up to 30% of the cement can actually be replaced using a high volume fly ash concrete, and where we can create up to about 120 megapascal concrete compressive strength, where utilizing industrial waste. Like this is a typical mixed design of a fly ash by percentage replacement by mass of cementitious material, 15% fly ash, and the fly ash type. This is the density of the concrete we obtain. The compressive strength at 28 days is about this level, with the Young's modulus of more than 40 gigapascal, where we actually use this to actually reduce the amount of the cement. Okay, so for vertical connection, we actually this is actually for vertical connection between modules. We actually have a concept. We have created concepts of a vertical tying rod with horizontal tying plates, and between for the modules, the concept. And also we also further improve by using grouted sleeve connector to replace the tension rod system. And this is a picture of how does the grouted sleeve connector works. And then you insert, and this is the outer part and the inner part, and this one is all the shear keys. Okay, and the receives by diagonal compression strut. And this grouted sleeve connection has been tested in an NUS lab, and analytical prediction with test results are similar within 10%. And we also validate with finite element abacus. Okay, study on the picture shows on the this part of the inner part of the a rectangular hollow section in the outer part where there's so in the global analysis of the high-rise PPVC building, we actually created a modeling of 3 meter by 6.5 meter by 3.2 modules, and there are about 20 modules per floor. And this is a picture of a module of a 6 meter length by 3 meter width. We combine, stack it up together above a transfer plate. And the red color actually is a concrete shear wall, reinforced concrete shear wall. And we actually use a continuous semi-rigid diaphragm on a PPVC core system. And this is a picture showing the 4 modular units stacked up together and the connection concept. We actually use the column-to-column connection, okay, between the 2 units. Actually, this is 1 unit, this is another unit. We use actually a tie plate as earlier shown. And in our final element analysis, actually we model as a pin-pin connection to simulate a conservative connection. And for the column-to-column vertical connection, this actually is one PVC unit above. This is next door PPVC unit below, and there's a 20 mm gap. So this part here, the column-to-column vertical connection, actually we are using a threaded steel rod concept secured by a locking nut, and we model pin connection here, pin-ended connection to be conservative. So this the building actually is designed as per the Singapore code, and now as following the SSEN Eurocode 8 for buildings more than 20 meter, structures need to abide by a low ductility level seismic design, and the structural concrete design need to follow the Eurocode 2, and the structural steel follow the Eurocode 3. So basically the material property of the building we're talking about is the concrete core is about 50 megapascal, with Young's modulus of concrete as shown, and the steel we are using S355 steel. So basically for the first 20 story, we are using a composite column for concrete grade 50 with square hollow sections at the outer, and from level 20th the second half of the 20th story, we're actually using the square hollow section 300 by 300. And for each of the PPVC modules, we're actually using, for the long beam and short beam, we're using rectangular hollow sections 300 by 100 dimension, and steel beams of RHS 300 by 100. And the central core wall actually is 400 thick with a couplet wall, and the slab actually is 120 the reinforced concrete slab is 120 thick with a transfer floor plate of 3 meter. So the design consideration is that we use the wind action parameter for Singapore for 20 meter per second of a fundamental basic wind speed velocity, and followed the Singapore terrain factors, and also we catered for the Singapore National Annex for Eurocode 8 for the most conservative soil is a marine clay, and subjected to a peat bedrock acceleration of 0.175, structural bender of 5%. And this actually is a structural response spectrum that is input into the software, and with the concrete, the structural period is about 1.5, and with the site factor implication about 2.5. And actually we subjected the building to SLS load and the seismic load as shown here, where this part is the service limit state design is a dead load, the superimposed dead load, live load, wind load, and effective equivalent horizontal load due to geometric imperfection. And we also have subject the building to a seismic load combination, where we have a dead load component here, live load component in, and this is the earthquake load along the X and Y direction of the building at a different perpendicular direction of the building, and also equivalent horizontal load for geometric imperfection. So these are the results of analysis for the P delta. So we actually studied on the effect of the P delta analysis. So you can see that for the building actually at the weaker direction in the X direction, this shows the wind load at the x direction, and then with the addition of the p delta effect. Okay, so and also we did local analysis of the equivalent horizontal force also, and subjected to seismic load in the x direction, for example, without the equal horizontal force and with the equivalent horizontal force due to geometric imperfection. And this two graph actually shows is the seismic load in the y direction. Okay, these two graph here shows is the wind load in the y direction. These two shows the wind load in the x direction, and they are all within the service limit state deflection criteria for overall drift and interstory drift. And also Eurocode suggests for 50% reduction in stiffness to account for the concrete crack section. And we have actually studied to be conservative with the uncracked section at the core wall and with the 50% crack section. And this is the response of the 40-story building along the x direction and the y direction. Then overall, this actually is the load displacement curve due to a combined effect for the building. So you can see this part here is actually due to the seismic load combination. In Singapore, is more governing compared to the wind load combination, and actually is less than but the overall effect actually is less than the service limit state is being met. So the global analysis can be performed with the combined effect due to P delta equal horizontal load and concrete crack section. So where we actually use these modeling assumption in the connections of between the modular units and the continuous semi-rigid diaphragm. We found that it's reasonable for global building analysis, and we followed the local authority code for seismic and wind. So in summary, we have actually went through the advantages of the concrete composite system, which actually is lighter, longer span, lesser module, reduce, okay, and also we went through the global modeling where actually we assign a semi-rigid diaphragm connection and the conservative simplified model, and studied a combined effect due to P delta equal horizontal load reduction in crack stiffness. And this research actually supported by, we like to acknowledge the research actually supported by National Research Foundation, SEMCORP, and NUS. And this is the references. Earlier references actually were published in this area in the following journal papers and conference paper. Thank you for your time.